Yeah, he went super like.
Have me some markers. How's everyone feeling for the exam? Pretty good. Mostly it should just be, like what you guys were doing on the homework. But I want to make sure that you guys are understanding some concepts, because those concepts are really what's going to be tested on the exam. Russell hasn't showed me the exam yet, so I don't know what's on there. But if I were writing the exam, I know that the thing that I want to test you guys on is, do you know how diodes conduct? Do you know if I forward bias a diode or if I reverse bias a diode, what's going on? And do you guys know the small signal model for it? And then the same thing for BJTs. That's pretty much all those tests are. So if you guys remember questions like this one from homework. You know, this is a really important question to understand the in and outs of. Can you tell me what the KVL and KCL equations are for this? That's how you find ID, that's how you find VD. You can't just assume 0.7 volts across the diode. You got to find it. And you got two unknowns, you got VD and you got ID. That's it. So you build up your system of equations and then you solve. I don't know what you guys would prefer and work through some examples later, but I kind of want to go through concepts a bit more than just the straightforward problems. But
Sounds good.
all right. So, if we're approaching this problem, KVL and KCL, if I do something like this, it'd be a bit of a pain, but could you solve that? KCL equation is going to be a little bit more complicated. If I say that this diode's area is 25 times bigger, what does that change? Can you guys solve that?
And what the other? I think if they're in parallel, can I just combine the diode into one? With 26 times the area of the small one?
Mathematically, I think that would work, but I would be very careful about it.
Yeah, like assuming that, yeah, if that's possible, then do it.
I would say that is not a solid thing to attempt on the exam. If you want to do it in your own time to see if it works, then that's when I would do it. But on the exam, write them all out. Write them all out. You can, if you know for a fact that they combine. So if you go and you work it out and you have to prove it, then yes. But otherwise, I would stay safe and do them independently.
Okay.
Because you don't want to get into a situation where you think they're the same as parallel combinations of resistors, something like that. All right. Okay. So just going from a diode to the small signal model. I want to talk about some things there. And I can't remember if he talked about this in lecture or not, but G sub D and C sub D, are they physical values or are they just mathematical representation? Mathematical, right. G sub D and C sub D are not physical things, there are ways to describe a phenomenon. So it's the way that you describe how much forward transconductance you have. That's G sub D. And then C sub D is describing some stuff that's happening related to the way charges move. But they're not physical capacitance. Does everyone understand where junction capacitance comes from?
Where the junction is.
That you have a depletion region here. And this exists forward bias or reverse bias, no matter what, this depletion region is going to exist between the junctions. And the charge here and the charge here, you have a capacitance that comes from, and that's C sub J, right? So our small signal model ends up being those three values, C sub D, C sub J, R sub, or G sub D. And of those three, C sub J is a physical thing. The other two are just based on forward bias. They're related to the small signal, which is the derivative of current for C sub J and then, or C sub D, G sub D, and then the charge across the diode for C sub D. Okay. Did you guys understand bridging that gap to the model for the BJT? Where you have two small signal mono diodes and a current source in between. Okay. Talking about theirs. You have that. We're operating in the forward region, so this diode is reverse biased. This voltage is the highest point. This is higher than the emitter, but less so than the collector. So this is reverse bias. This one's forward bias. That's your forward operating region. So if you do the small signal model for that, you have between the base and the collector, you just have C sub J.
Or a resistor.
Yes. Talk about that. But we understand where these four come from.
I have a question about that. Like, why isn't there a resistor next to the distance of on top? Like,
Okay, you're talking about the R mu. So, I know there's also, in some of the problems you have this R mu. Right. That is going to be this voltage. So V over I.
Okay.
Which ideally you would want very little current going from your collector to your base. So ideally, this is input. It's not always, but that's where that relationship comes from, and that is the same type of thing that you get for this RO. You look in the materials, you'll see that the derivation ends up being that the VCE or ICE gives you RO. That's true for any resistance that you want to look at. If you want to look at your resistance looking into a circuit or at the output of a circuit, you take that input voltage divided by the input current, that's your input resistance. The output here or R0 is of the collector emitter voltage and current relationship. So conceptually, that's where this exam is, or should be. Do you guys have any questions on this?
Would Russell care if we add the capacitor that equals 0?
Tell me that it equals 0, that's good. You know why it equals 0?
To be honest, no.
Okay.
But I was just wondering because I think I remember him mentioning going over the small signal for the one of those questions on the problem set. I do remember I don't know if he switched it up because then I watched the next lecture. He said something else, but he said he would want you to include the capacitor. If it includes them. The other resistance is like bar prime B. Yeah. He also said he wanted to see those two, but I don't know if he doesn't care or.
It'll, for R prime, B prime, C prime, those will be specified in the problem. Those are like your contacts. So when you make a transistor, you put a lead onto it, onto the terminals, and those have resistances. So that's your R prime, B prime, C prime. It's just like a non-ideal thing. In some of the problem set too, some of those problems said specifically that those would be 0. It's typically what you'd see on the exam question too. If it's not 0, then you include them, but it's not usually going to be.
They are given, still put them on small.
You can. I care more about if you guys understand why they're there. So big thing is not just copying like the same shape, but understanding why that shape exists. So for example, like C sub D, between here, that capacitance that is 0 is 0 because it's in reverse bias. And there's no movement of charges the same way as there would be in forward bias. That movement of charges is what causes C sub D to exist. So big thing to remember is just C sub J is the only small signal value there that exists in reverse bias.
Could you talk a little bit more about the C sub D and just like where that comes from?
That one's definitely tricky, and I'll do my best. But I also do recommend going to office hours for Russell, and his office hours say 5 a.m. But if you catch him at like 10:50, he gets out of circuits 1. At 10:50, you can go upstairs and catch him.
And by the way, the building is locked.
You can email him.
Yeah,
Yeah.
email.
Well, what I did is I found a door that was not locked.
The Was it what happened? Was there like,
What there was
Something-
on that side?
there, the other night, someone put like one of the wet floor signs in between where the door is closed.
I don't really mean wet floor sign there, but
We took it out. It was late. Why was it there? Why was I?
Trying to get back inside.
No, we were leaving.
I'm saying, can you put that somewhere there? Let me go McDonald's.
So this is in the chapter 3 or chapter 1, 1993. Page 10 is where they have the expression of Q sub D. The charge generated and stored in the neutral region. That's a function of your voltage. Involves some hyperbolic functions. So if you want to take the derivative of that, you're free to. I don't necessarily. But the derivative of that is what gives you your C sub D. And it turns out to be an exponential. That's why it's only in forward bias. Because exponential and reverse bias would be 0.
So charge with respect to what? The derivative charge with respect
To the voltage across the type. That becomes exponential. And that, you reverse bias it, you have a negative exponent, it's going to be 0 or approach 0.
On the first picture you draw, this first surface you draw, how do you use the PVL to you solve that?
Yeah. Are you guys good to erase?
Yes.
Do you guys want to do this with numbers or do you guys want to do it just expression wise? Expression wise, great. I don't want to do numbers.
They're gross.
I agree. So, I was thinking what you need is. Even that's about the information that you'll be given. Maybe some small signal model stuff.
I sub G equal to S.
I sub S1
Oh, I sub.
is equal to 25 times I sub S2.
IS2 is 25 times larger than diode 1.
Yeah. So from that, you can start
Other way
building
around.
up.
IS1 is 25 times bigger than IS2.
Right?
No.
It should be the other way.
Oh,
Yeah,
yeah.
it should be.
Okay.
yeah, because bigger area would mean bigger current.
Or which one do you guys want to start with, current or
KVL.
Current. Or,
typical? ACL %. From this, what can we get?
There's node at the top. Yep. So current from EG R1, so call it I1 going in. Then I2 down D1 out. R2. So IR1 is equal to ID1 plus IR2 plus IG2.
Not me.
I know, it's not you.
Okay. APL. With some quick things that you can say about the voltages that are pretty important. Circuit wise, what voltages are the same? And what should the KVL add up to?
The diode voltages are probably, and that one, the resistor in the middle are gonna be the same.
Voltages in parallel that are gonna be the same, so
Yeah, same drop across all of them.
V1 equals VR. And then our KVL equation there is gonna be
EG is equal to VR1 plus whichever one of those.
so from there. We can find equations for each of these currents. So we can say that IR1 equal to VR1 for R1. And say that ID1 equal to
Exponential.
Bracket.
okay.
Yeah, ED1 Ada.
Beta thermal.
Which I know in the solutions he will drop the line a lot. Do that. I like to be more precise. It's nice to be more precise. I'm not going to count you off.
If he said bigger than one,
Yeah.
greater than one, we can say the one. Something like that.
Well, if it's like magnitudes greater.
Yeah, if it's like, you know,
It's an exponential.
Yeah.
It'll be big. You can take one away and not change it too much. I do 2.
Wouldn't it be the other way around? Didn't the ID1 equation have the 25?
Mhm. Mhm.
those three voltages are the same. And you can get this voltage in terms of that one from your KVL. Then you should be able to solve it. Plug it back into your KCL. Solve for VD, and you can solve for the currents.
No, I just need one value for the voltage.
You need a value for IS, VD, ADA, the resistors, and G. Those would be given. That's a pretty common type of problem. I could give you it with 3 diodes. I could give it with 2 diodes and then 1 diode on top. I could give it 3 diodes in parallel. Or I could put another diode here. Should be more pain, but I think at max there would be 3. But that's basically that problem, is can you set up KVL and KCL with stuff that isn't just a resistor? And don't just assume VD, don't just assume a current. Good. If I gave you a current source, do you guys think that you could do that? Instead of a voltage source, if I gave you a current source and then asked you to find the voltage. It's the same process, but now you would know this one. We would be able to get something from here, plug it into here.
DR1 is not supposed to be circle, right?
I'm saying that you could get that from over here in terms of the other ones.
So for clarification, whenever there's like diode problems like that, there's not any combination that's gonna need to happen, or it's just KVL and KCL.
Yeah, if he gave you guys a combination, like that for y'all.
Don't try to combine diodes.
I wouldn't. I'm sure it works out fine, but just to be on the safe side, I would need to work out on an example to make sure. That's it. Because if IS is the same and everything else is the same, then yes, but what if they have different ADAs? Can't combine them. All right. But good for everyone. Talk about real quick what to use for the small signal. Hopefully this clears up some too.
BJTs and diodes.
So does everyone understand what is meant by like your DC operating point? we either set a voltage or we set a current. And that is where we're gonna operate at. Right? So. You know, I'll write something for BJTs, you'll see IDQ a lot. ID quiescent, and that's your operating point. And then the small signal stuff that he adds on top of it is the derivative of this. At that point. Because if we wanted to approximate, say we changed it by like 0.002 millivolts, we'd have like a small increase here. You could go up and see on this slope. And you could approximate it to be there, the new ID. That's what that small signal is all for. Is just seeing small changes and approximation of where you're at. So when you're calculating G sub D, you take the derivative of ID.
Do we need to show the steps for derivative? Or just
No, yeah, it's gonna be cool.
the Taylor series?
Hmm?
For Taylor series,
No.
Gave us what.
Yeah.
yeah, just for it.
Yeah, you can just leave it, that's fine. It's just more conceptually, do you understand where it's coming from? If you do, that's good. If you understand just up to this bit, then you're good too. For this is gonna be same thing, IS. This turns into D. So what's the ID value that you would use to get from this circuit? The ID value that's going through here, that's what you put up. That's how it works for all of the small signal models. So that is the same way. Those come from their derivatives in the materials. And what you're doing is you're taking the operating value, the actual value that it's biased in, the actual current and the actual voltage, and you're taking the derivative and then using those values to get their D sub D, C sub D, all that. How do you guys feel about the last three problems?
The last one, 502 was a bit of a.
Is that the plus 80 millivolts one?
Yes.
About the other ones? Did you guys understand how to use that chart? Yeah, where it had the test conditions and that tells you what they are a bit more. That ties into what we were just saying here. You know, those test conditions, if they tell you IS, they got IS by reverse biasing it a lot. And that value is just what they're using there. And that is what you can use for IS. VAF doesn't usually give it what your circuit is biased at. So did you guys have any issues there with those? If you see a VT on, so I know the materials are, some of them will leave out the ADA, like D sub M in the materials is sometimes written as this. Right? It should have the ADA. In the materials, I think he did the derivations with ideal, so ADA is one. But the same thing for the diode equation where ADA is in the exponent, ADA is in the exponent for the BJTs. That do you guys want to cover anything in specifics?
Could you cover the test condition from the lottery question? How that work?
Yeah.
What goes up? Actually, back on.
Yeah, so I guess on the math fundamentals, the professors have a lot of typos. Like slopey writing. And then since it ends abruptly.
Please,
You guys see that?
filter.
The projector.
Can we
like,
talk to
filter.
maintenance about that?
I can do that right now.
No, you're fine. That's a me job.
Lights on, lights off.
Oh,
Okay.
that's it.
Okay. I'm talking about here with IS. If you want to get an accurate value of IS, you just reverse bias the junction. And just see how much leakage current getting through it. So that's how they give you a value of IS. But that is the IS value that you would use in your IC equation. FT, that goes into the materials. We'll talk about that in a minute. If you look at the circuit, you have VBE is 0.65 and VC is 5 volts. So here, they're giving you the VAF for that. Which, does everyone know what early voltage is coming from? We have this slope.
The starting point, right? The starting point.
Pull it down quickly. Quickly pull it down.
Right. Ideal current sources could supply the same amount of current no matter what voltage. But you take the relationship between voltage and current for that, the slope of V over I, the output resistance of this would be infinite. That is where the ideal current source sort of model comes from. BJTs are considered current sources. So BJTs, however, they're not ideal. Ideally, after you get them turned on, they would supply the same amount of current no matter what the collector emitter voltage was. But they're not ideal, so they have a slope here. They have a finite output resistance. And you can characterize that by taking this slope all the way back here. This point, negative VAS. That's where early voltage comes from. It's from slope of the collector current. VC. What does that mean in practical terms? It means that as you increase VCE, IC should increase too, independently of what VBE is. You see that in the equation where IC equals IS X1. This is times 1 plus. If the BJT is ideal, VAF is infinite. Because the slope would never touch the voltage. So if VA is infinite, then your IC equation only depends on VBE. But in a non-ideal case, IC also depends on your collector emitter voltage.
Is it like the absolute value of VAF since it's negative?
Yeah, you'll be given. This point is negative VAF. It's just a positive value that you're given. But yeah, absolute value. Does that make sense? And then with these test conditions, What did they give us? What are these?
Junction, capacitance for emitter.
Yeah,
Correct.
but with the bias conditions, it's 0 bias, so that's CJC0 and CJE0. So that you can use to then get your CJC and your CJE at whatever value you got for the junction voltage. Makes sense there? Oh, and be careful with CJC because it's the base collector voltage, right? I don't know if anyone knows how to do it, but if you guys figure out how to use OSR, I highly recommend it. Use someone who OSR. It's a way to get PDF files read by the computer so that it recognizes text.
Oh, yeah, I guess I agree. I kind of wish that this PDF doesn't give out searchable PDFs.
Yeah, you OSR it and then it becomes a searchable PDF.
If someone figures that out, let me know and we will get a USB and we will supply it to y'all. But I don't know how to do it, otherwise I would have done it.
It won't work on all of his handwriting. But it'll work on a good portion of chapter 1, 1993. That one's not searchable, but it's text, so. That one's a good one to focus on. Okay. I don't know if you guys were able to catch this on the homework. Definitely was not obvious to me when I was doing it. But this frequency stuff that he was giving, this FT. You can use it to find CD. Omega T, where the pointer is, it's 2 pi FT. So you can use that equation. Again, this gets into some more of that knowledge where CTE is not an actual capacitance. It's like a mathematical representation of a certain phenomenon. The derivation that's coming beforehand explains that and how you can derive it from these frequencies. Not necessarily super important, but a reading material and go ask Russell, you can. Does anyone have any problems from the first problem set today? Kind of remember, don't fully understand. think you guys were given one where you had different bias points and you had different capacitances. This one's similar. Yeah. I give you two different capacitance values. Can we find CJ0? That's one that comes up a lot. Oh, out of the diode questions, that's definitely one that you can ask. Right. Already almost an hour, so. Any questions? Also be about where the course is headed.
Did we take electronics too?
I love electronics too. I don't know if you will, but I think it's a good time.
Like that kind of have to, right?
No, it's an elective.
It's an elective. So if you want to go do a master's program, your master's program might have you to redo it. Depends on the school. I liked it. It's a little bit more relaxed, a little bit more understanding. It's what you're actually learning. So it has a lab, but it's not like your other lab where a lab is due every week. It's, do you actually understand it? Do you have it finished? That's when it's due.
Well, so for sophomore design, I know the workbenches have key lock, but everyone has the same keys. It,
Yeah, the keys unlock every single.
that's
Bunch up
reading the
there?
purpose of. They're in a room that's belong, so.
Yeah.
Oh, it's security theater. I think
Just watch through this way capacitor. You didn't have to do a.
I've been watching. I've had this shirt like
Some people just like.
this whole, I've had this shirt since like last
There's some people,
Christmas.
no, there's some people that just like the design of certain shirts,
That's
but they don't
very
know what
fair.
it is, they just wear it.
Thursday at 7, I think so. You come in? Yeah, that's what it says. If you come in.
Good luck tomorrow.
I'm working Wednesday. I'm on John going.
Good luck. Thank you. Thank you.
It's good. It's definitely good. I mean, it's only good. I have.